Dr. Todd Gillam is a postdoctoral researcher at the Future Industries Institute at the University of South Australia. Todd's project is formation of MIP particle films on substrate and successful detection of flotation frothers via gravimetric detection. Todd's childhood hobby was collecting gems and minerals. He is a competitive field archer, and before pursuing a career in science, he was a skilled labourer. He's currently using those skills to renovate his first home. Todd.
Thank you. Nice big green button. Okay, so I'm working within the Downstream Processes Program B on Research Project 7, which involves the development of a sensor for the inline monitoring of froth flotation agents in flotation processes. So to date, the key findings of this research are that we are able to develop materials that interact with these key components of frother mixtures through an adsorption process. We've developed a series of polymers that we're evaluating for their binding properties to these components, and we believe that this will lead on to the development of a successful coating for a Quartz Crystal Microbalance platform for real-time monitoring of these components in flotation processes. So briefly, an overview of flotation to a population of people who know more about it than myself. Basically, you have a bath full of bubbles, which are decorated with these hydrophobic components, and you have binding of copper sulfate minerals to these bubbles as mediated by an ethyl xanthate collector. What we rely on in how we're going to tackle this problem is based on molecular complementarity. So we want to develop a system where we have complementarity between the binding properties of our target molecules and the polymers that we create. And a typical way of achieving this within food industries is to employ molecularly imprinted polymers, where you'll take a template molecule and you'll select compounds that interact with key features of that molecule, and you'll polymerize a backbone based on that to form these sockets that will bind these components in solutions and allow for sort of gravimetric analysis if you then adopt that onto a QCM through a mediation of binding and desorption from these materials. So that's the central premise for how the materials in this project work. And then with successful materials being made, moving forward, we will coat these quartz crystal microbalances, and adsorption of these key molecules within the flotation baths with the substrate surface will induce a difference in the frequency of this monitoring system, which can be correlated to concentration in real time. However, the compounds that we're targeting here within the interfloat frother mixture are quite simple. They don't feature distinct chemical handles that have a high degree of specific complementarity to available monomers when we're designing and creating these polymers. Instead, they're typically straight chain or cyclic alcohols or polyglycols that feature a hydrophobic component. So really the only handle that we have to work here is their hydrophobicity. Some other work that I do on medicinal chemistry projects uses cyclodextrins as a platform for various reasons. These are no strangers to the pharmaceutical industry. The benefit to using cyclodextrins is that they are polyglycosidal macrocycles, and they have a hydrophobic cavity orientated towards the inner circle. So like a hoop with a sensory ring in it that is going to bind each of these things. On the outside is a very hydrophilic rim that allows for access of simple chemistry to add on clickable handles or polymerizable groups. So we were able to take this as a platform and produce a material that's going to be able to interact with these components based on the formation of hydrophobic inclusion complexes as demonstrated here with the binding of cyclohexanol within the cleft of beta-cyclodextrin. Cyclodextrins have different sizes depending on how many sugars are in their ring. Beta-cyclodextrin was selected as we believed it had a good size complementarity to cyclohexanol, and we were kind of hoping that we might get some degree of selectivity for that component just based on that steric bulk. We didn't really achieve that, but that's life. So here's some nuclear magnetic resonance spectra of beta-cyclodextrin and cyclohexanol, and these are just to demonstrate the principle of binding. Basically, in the red trace, you have the protons relating to cyclohexanol. In the green, you have beta-cyclodextrin. And then when you mix them together in blue, you can see a shift in key resonances which correlate to the H3 and H5 protons of the sugars within the ring that make up the hydrophobic surface of beta-cyclodextrin. This is a means of confirming that you have complexation with your host molecule, your guest molecule within your host. So we screened all the components that are in the interfloat mixture and could determine that of the 4 that we're targeting, they form these complexes. The next step is you need something that's not just going to dissolve in water like beta-cyclodextrin does, and you need it to be a viable material platform that you can take forward for binding and development onto the Quartz Crystal Microbalance system. To do this, I formed a highly cross-linked polymer network using epichlorohydrin, where basically I formed a reactive epoxide intermediate out of the beta-cyclodextrin unit and formed this highly cross-linked but porous water-insoluble polymer, which looks like this snotty boy on the right-hand side there. Basically, when we first made these, it was produced as a large sort of monolithic structure, which required a lot of grinding. It was kind of hard to work with. These were quite large, which was ultimately not suitable for further adaptation down to the Quartz Crystal Microbalance system. But we started to evaluate their adsorption properties, and we can see that they're interacting with the components that we want in a sort of scale that would be useful. So the next step here was to try and reduce the size of these particles a little bit. So I've introduced an emulsifying agent, being lauric acid, into my synthesis here, and was able to form it as more of a particle suspension. So rather than getting a big block at the end of it, I got a collection of fine powder. Again, some of these are still approaching sizes that are a little bit large, but for the most part, we got a production of much smaller population of particles, which I have some laser diffraction size determinations shown on the left-hand side here. I won't labour the point of those too much, but and I've got a depiction of some of the particles through SEM micrographs. So basically the properties of adsorption are retained in these polymers, and with ongoing work we're trying to reduce the size or platform that we're using, still using cyclodextrins, trying to achieve a smaller particle size, and we've been evaluating them under different conditions like temperature and pH and seeing how that might modulate selectivity for the individual components of the interfloat mixture. With future work moving forward, there's several things to be achieved. Ultimately, I'll continue to evaluate the performance of these sorts of materials. Overcoming size constraints is still a major consideration. To tackle this, I've recently been producing magnetic nanoparticles, which are decorated with the beta-cyclodextrin. This drastically reduces the size of the platform, but they do retain the same adsorption properties, and you also have the benefit of being able to handle them magnetically, which can be a great benefit for processing time when evaluating these materials. I then need to determine if selectivity can be modulated somehow for these systems. It may be a limitation if we are detecting too many things at once within a solution. Having some selectivity for individual components would therefore be a benefit. And I may be able to achieve this through possibly substituting out the cyclodextrins or modifying their rim to cause some sort of exclusionary basis for selectivity. Once we have a suitable material, we'll then go on towards fabrication of the QCM for inline sensing and assess its performance. I'd just like to acknowledge our team members, Bill Skinner, Marta Krasowska, David Beattie, and Anton Blanco, who's my line manager. I've also had several research placement students on this project, which has taken sort of several avenues to date. So Olivia Mastro-Domenico, Emma Marchson, Ashlyn Austin, and Emma Pearce have all contributed to this work. And my industry partner is Magato. Thank you.
Any questions for Todd?
It's okay if not.
Don't get off the hook that easily. Just wondering about applications beyond mineral processing for this kind of work. Can you enlighten us on that?
Yes. So because beta-cyclodextrins are largely employed for the detection of polycyclic materials, within a frothing scenario, they're not really a concern as for contamination. But if you were to take these polymers or materials to soil reclamation, monitoring of environmental pollution, the detection of steroids in wastewater, I'm sure they would all have utility in those fields.
Just following on from that question, so froth is normally, if you're adding too much froth, it makes a mess. If you don't add enough, there's not enough froth. You looked at stuff like this, have you considered it for collectors potentially, where overdosing of collectors is not quite as obvious?
Yeah, I've been considering some options for monitoring the collectors. It's a little bit more tricky at this point in time. So either we need something that has a high degree of complementarity to the xanthate itself, and initially I thought perhaps we could develop some responsive metal ion complexes which work on the principle of chelation by the xanthate for a spectroscopic response. I need to look at whether the xanthate interacts at all with the beta-cyclodextrin systems, though I doubt that it would have a hydrophobic interaction because of the short chain length of ethyl xanthate, but possibly larger xanthates might. But I think it would need a different sort of solution or a different way of tackling that.
Thanks.
No worries. I hope that answered the question. Yeah, cool.
Okay, thank you very much, Todd.
I think I have to say this. Go and put some sugars in your room.
To wrap up Program B, we will hear from Dr. Richmond Asamoah, a postdoctoral research fellow of Minerals and Resources Engineering at the Future Industries Institute at the University of South Australia. Richmond is the king of multitasking. He's conducting 5 translation projects and supervises 2 research projects. Richmond has over 12 years in-depth knowledge and hands-on experience in mineral processing and extractive metallurgy. Richmond holds a Bachelor of Science with Honours in Minerals Engineering and a PhD in Engineering, Minerals and Resources from the University of Mines and Technology and the University of South Australia, respectively. His research interests are physical separation and beneficiation of complex mineral ores, hydromet, machine learning, data analytics and process optimisation. Richmond.
Thank you very much, Ruth. Good afternoon, ladies and gentlemen. So my talk today, I'll introduce you to the translation projects in Program B and provide you with an overview of each translation project and how they are linked with the research projects in the consortium. I'll then indicate our current findings and future work based on the major activities that have been agreed upon by our translation partners and our end user. So the mining industry, specifically mineral processing and extractive value chain, is very complicated. Having each unit operation or each unit performance defined by several sub-processes, fundamental sub-processes. So that is already complicated. And this is further exacerbated by the heterogeneity of the ore. So the ore that we send to the mine or the downstream process is not consistent, it's not homogeneous. You can have hard ore going in today, tomorrow it differs. So you have different sizes or different mineralogy going in. So that complicates the process. But with current advanced techniques and instrumentation, we can develop more sophisticated approach which can simplify the human process interface and help us to maximize the metal production. So in Program B, in line with that, we have 5 translation projects, and these are linked with the research projects in the consortium, the excellent talks that you've heard throughout the day this afternoon. And these projects are from the grinding circuit down to the tail sleeve circuit and are led directly by our translation partners, Manta Controls and Magato. Specifically, the first 2 translation projects, which is TP7, the ones in yellow, TP7 and TP8, translation project 8, are led by Manta Controls, and the projects TP9, 10, 11 are led by Magato. So within the communication group, down there is the translation project 7, and this is focused on improving the autogenous and semi-autogenous grinding, and through optimization and stability of the autogenous and semi-autogenous process, and also to maximize the mill throughput by installing an acoustic sensor in specifically the Manta mic acoustic analyzer in the grinding circuit. So why is this important, and what are some of our important findings so far? We've been able to locate a location on in the grinding circuit where we can install the acoustic sensor, and that is very important because based on where the sensor is, that determines the information we can get and the usefulness of that information in the control of the grinding circuit. Also, we've done preliminary studies where we have been able to establish relationship between the acoustic sensors, data that we've obtained from Manta Controls, where we have about 33 different frequencies, acoustic frequencies from operation, to establish relationship between the acoustic frequency and also mill operating variables such as the mill weight, the mill speed, and some of the things I'll dive more into it as I go through the presentation. The focus of this translation project is to address key challenges, key specific industry challenges. And the first one being decreasing ore grades. This is not only limited to copper, but it's a global challenge with metal commodity. But decreasing ore grade is one of the key challenges there, where unlike in the past or the good old days where you have high grades, 15%, I'm going grams per ton, which is in the gold, but 15% of copper grade, that means that you can treat 100 grams of the ore and you obtain about 15 grams of copper. Now you're working around low grades 1%. We saw the graph that Gavin showed, even lower than 1%. So that means that you are treating the same 100 grams, but you're obtaining just 1 gram of copper. So it means that for you to maintain productivity, you need to now produce or treat about 15 times the amount of material that you have to use to meet the same amount or the same output that you were getting in the past. So that is, we need to maximize our throughput, which is very important. And as was mentioned earlier in the start of the talk by Kweku, the grinding circuit represents a very high energy consumption section in the mineral processing chain. So you consuming the greatest percentage of energy when you're milling. And that means that for us to benefit more, we can increase our throughput, and then we are reducing the specific energy that is required for that processing. And the other challenge is operational stability. It's very difficult to maintain a stable operation. This is mainly due to the varying mineralogies or the ore characteristics that are being fed into the mill. So you can have, say, a hard ore that is being fed into the mill, and you use specific set of operating conditions for that ore. When the ore gets softer, that condition is not suitable again. So you need to vary it, and that causes instability in the operation. So sometimes in a typical curve where you have load to power curve, which is being used to monitor the performance or the stability of the mill, every operator wants to make sure they are working below that point where you tip off over to the unstable region, so that you don't fall off. So that also means that you are not meeting the maximum capacity of that particular operation. So these are major challenges, and we are anticipating that by installing this sensor, we can be able to collect useful data, which can help us to improve the optimization of the mill, the autogenous mill, and also reduce the specific energy, and also have an optimum yield of particle size, which is useful for the downstream operation. And this translation project has been divided into 6 major phases. The first one is to assess the location on plant. So that goes up to phase 5, where we're currently developing the models. We've done preliminary work on that, which I'll share some of the things we've seen there as well. But then also to build the Manta mic, install it on site, and collect data from that and use it to build the models. The phase 6 is mainly collecting additional data, refining the models, and using it, getting better information from that. So this shows the location. So at BHP Olympic Dam, which has been our main focus there, there are 2 primary mills. We have the Fuller and the Sfadella mill. So the Fuller mill treats about maximum about 400 tons per hour of material, whilst the Sfadella mill treats about 800 tons per hour. So our focus will be on the Sfadella mill, and we've assessed that we can have 2 microphones on the mill, one at the eastern and one at the western part of the mill, just because that mill operates in 2 directions. So in case where we have it running in a clockwise direction, we're still able to get information from the toe of the mill, and when it's running in the anti-clockwise direction, we can still get information, which is useful. And for the analyzer, that will be installed in the substation. So that was successful. And the other thing that we've seen from the preliminary data that we've received is that we are able to use the frequency data to correlate or link it with the mill operating conditions, such as the mill weight and the mill speed. And that is very important, because some of the things that Kweku shared about changing all feed characteristics, where the hardness is being seen in the acoustic information, or the sizes are being seen in the acoustic information, we can now be able to probe further into those regimes or those phases and work on plants to get those information. Here, what I've shown is the mill load. And we've developed models that could predict the mill load, and you get very good results from that. Both the predicted and the measured information looks very good. And again, when you look at the curve there where we have the variable importance, we could see that different frequencies that were used for the model development play different roles, and their sensitivity or their weighting varies in the model. So that is also very good. With different operating variables, our observation is that when we subject the same set of data we've collected, different frequencies were reporting, playing different major role in that. So we can use feature selection techniques to select the critical frequencies that are very useful for a particular operating variable, and then build the model that is useful for that. And again, with the help of the functional relationships, we can set up thresholds within that frequency and use it to get the sweet spot or get the right information for our model, or detect errors when we have the data coming in. So I'll now move, still within the grinding circuit, move to the translation project 8. Now, this translation project 8 is also led by Manta Controls, and the focus is to install particle size monitor on the hydrocyclone, so the hydrocyclone overflow. And this is very important because particle size has been one of the major variables that every metallurgist knows that in the downstream flotation, or even if you go straight to the leaching circuit, it's very critical. It's very important. So but monitoring that on site, however, has not been very frequent. And so having a sensor on site that can monitor the particle size continuously in real time, and using that information to feed back into the control loop or the control system is very important. Now, In terms of flotation, you are trying to work within a particular range, say from 30 to 106 or 150 microns, which is the best for your flotation, but based on the mechanical cells that are used on plant. But when you get it too coarse or you use too fine material going to the flotation, you end up losing it to the tailings. So that is not the best option there. So you have to be able to monitor the particle size. Now on site, usually what is done is there is you monitor mainly the particular value, say the P80, which is 80% percent size. So say P80, 80% percent, 75 microns, for instance. So an operator on site will monitor just the 80% percent size, which is 75 microns, and based on that estimate or assume that you get a particular outcome in your flotation. But the flotation process, which is more sensitive to the variation in the distribution of the size, will yield different outcome. So having a knowledge of the distribution is also very important, not just the single value. And on-site measuring of particle size is also difficult because it's laborious, manual, so it means more cost. So having a sensor that can do that is very useful. So this is the purpose of this, and this work is directly linked with what you've listened to this afternoon defense talk, research project, and it's also led by Manta Controls. So what are some of our findings? We've able to also identify a location on plant where we can install the particle size monitor after several search for a suitable location, and I'll show you that in a few minutes' time. But this work also focused on addressing key end-user challenges. The first one being decreasing ore grades. I'll not go back into that because we talked about it earlier in the previous one, but also overgrinding, ore overgrinding. So in the hydrocyclone, the focus is to separate the fine particles into the downstream process through the overflow, and also the coarse particles back into the mill. When you have the cyclone not performing properly, you end up having coarse particles reporting in the overflow. That is typically referred to as roping. And so the coarse particles report in the overflow, and the fine particles report in the underflow, and that goes back into the mill. When that happens, the amount of new feed that you need to put into the mill reduces. So then you are reducing your throughput of the mill, and you are overgrinding that fine particle, now separating it back into the flotation circuit, and eventually that will go to tailings, because it is too fine for the flotation to be able to separate it. So you are losing material, you are losing energy, you are spending a lot of money in that. So being able to monitor that hydrocyclone overflow is very critical, is very important. And also intermittent poor flotation response, which is something that is not usually, is a major challenge as well, because when the flotation is working today and the feed that comes in varies based on the particle size, as I've mentioned, or the pulp chemistry variation, mineralogy, as was mentioned also as well today, you tend to have poor flotation. So this challenge was the main focus to be addressed with this translation project. So we are anticipating that with this translation project, or installing the sensor on site, we will be able to know the state of the concentrator. So know what is the state of that concentrator at a particular time. Is it working properly? Do we need to adjust something? Do we need to increase the density of the feed going to the hydrocyclone, or do we need to maintain the whole hydrocyclone? Do we need to work on it? So what is the state of the concentrator? That is some information we can get from that. And also we can improve our mill throughput and also copper recovery. Like I mentioned, when your coarse particles are supposed to go back in, you end up having fines in. When that happens, you can't get more material through. So by installing this, we can have a better grip on that and also increase our energy efficiency. So we can have higher throughputs and also reduce our specific energy consumption in the grinding mill. So again, this work was also divided into 6 main phases. The first one was to look for a location on site where we can install the sensor, which has been completed and successful, and then acquire the sensor and install it on site and collect data from that, build models that are useful that can be fed into the control system, and then continue to retrain that model with additional data set. Now, the 2 translation projects are led by Manta Controls. Manta Controls already have their Manta Cube at Olympic Dam, so linking all these into the control system is pretty easier. So this on the location for the particle size monitor. Initially, our primary target will be the Spadella mill. We'll focus on that. circuit overflow. But we investigated each circuit, the fuller circuit, the spherular circuit, to look for a location for each of them. And we also checked the OSA sample where everything goes in and samples are taken for the particle size, for this assay. So we checked that as well, and we realized that ahead of the track screen appeared to be the best option. And that was also good because we had other services like the water required to feed into the sensor and other things very close. And also, again, we can now at that point measure not only the fuller circuit overflow, but also we can measure the spherular circuit overflow. And that is very good. So we can use one instrument at that point and measure two streams at the same time. I'll move on because of time as well to the Translation Project 9. This Translation Project 9 is led by Magato. So I'm moving on to the Magato-led projects. And this project is focused on installing the pulp chemistry monitor in the flotation circuit, and then to improve the flotation performance. So major findings for this includes we've been able to install the pulp chemistry on site after assessment of a suitable location. We've also received an initial data set for the pulp chemistry data. And also I'll show you some things on the model selected variables which we use in the predictive analysis and how it is important to know which variables are selected for the input for the predictive model and its robustness or reliability of the model. So again, this project focused on addressing key challenges such as less predictable flotation response. As I mentioned earlier, won't dive into that. Currently, again, on site, these variables or sensors are for instance, the pH is being measured on site, but not more frequent. It's less frequent. So having a proper instrumentation on site which can be used to measure the pulp chemistry, specifically looking at the pulp pH, the redox potential, looking at dissolved oxygen, the oxygen demand, and temperature will be very useful. And again, poor interplay between copper recovery and target grade. So for instance, if we take the smelter, there is a target grade that is required for the smelter. So it's difficult when you have unstable operation to be able to meet that target grade and also meet a particular feed mass or recovery. So having a sensor in place that can help us have a better grip on the flotation circuit will be very useful. Previous work that was done in UniSA as well have shown that you could have heteroagglomeration between gang minerals, for instance, chalcocite and sericite. Fine chalcocite, sericite going into the concentrate or Froth zone. And that is dependent on the pulp chemistry. So knowing the pulp chemistry and again the change in feed mineralogy which is responding in the pulp chemistry, using that information to dynamically control the flotation circuit will be very useful. So having this sensor on board will be addressing issues such as improved flotation circuit optimization, copper mineral selectivity, maximize copper production, and reduce waste in energy, water, reagents use, and that is we are lowering the operating cost, and also improve downstream unit performance through consistent feed that is going to downstream. A change in mineralogy in the feed going to downstream can have a huge impact on the downstream unit performance, and that's something I've studied as part of my PhD as well. So an enhanced grinding and flotation circuit integration. So once we have these sensors on board, we can better integrate both the flotation circuit and also the grinding circuit. Before I go on from here, a new development with the pulp chemistry sensor is that it's now being renamed. So previously it's a pulp chemistry monitor. Now it is called Magopulp. We can talk about that afterwards. So, but this project is all divided into 5 major phases. We've been able to complete up to phase 4, where we're developing initial models. We've installed that on site and also have collected data, which is being used as part of work that Bismarck is doing as well, developing models, predictive models. So this where the pulp chemistry monitor is on site is in a rougher circuit. So when you get chance to go to BHP Olympic Dam site, try and pass through, and you see it running, very busy, working, collecting pulp chemistry data. And we also been able to get initial information. So from this slide, we've done some preliminary study where we randomly selected variables, input variables, which were used to develop predictive model. And we observed that as the distribution of the testing data set was the same as the training data set, you get very good response and good performance of the model. And when we move on to, say, a new data set and seen data set, which is pretty much distributing different distribution or is showing different distribution, the performance or the reliability of the model then begin to change. In the 2020 data set, it appeared to be working better than the 2019, but this is just because of the input variables that were used. So the causal relationship between the variables that are used and also their response, a target variable that we are trying to measure. So getting the pulp chemistry sensor on board, where we know that pulp chemistry also plays a role on the target recovery, will be very important and useful. I'll go straight to the Translation Project 10, and this Translation Project 10 seeks to investigate the MOF sensor, metal organic framework sensor that was presented this afternoon in real leaching systems and for the tails leach circuit. So we've been able to design a new reactor system at UniSA, which we will be using for the real system leaching, and that is to mimic the on-plant studies, and also have investigated the effects of pulp mineralogy on the leaching process. And this translation project is to address key challenges such as pulp gelation, and this is very important because in the uranium leaching you need a ferric ion to help oxidize the uraninite or the uranium mineral in the leaching process. But if you don't have enough of the ferric ion, usually what is used to detect or to monitor that is the redox potential, but the most critical parameter is the ferric ion in there. So on plants, you just end up dosing a lot of oxidants in there to move up the redox potential to get up to a particular target value. But what happens then is that when you do that, you are now leaching at very aggressive conditions, and that can cause other species to also dissolve in the solution, so and enhance pulp gelation. So that's a major issue which we are trying to properly monitor when we have a sensor of this sort. Currently, because of the leaching environment that is used for uranium, which is highly acidic, pH 1 and also high temperatures, you don't have a suitable sensor that can be installed or used to monitor this continuously. It will just break down. So having a MOF sensor, which is very effective in that system, will be very useful and can help in controlling the process. So that is linked directly to the benefits that we can get from this translation project to maximize uranium leaching whilst we reduce the gelation, pulp gelation, and also have a proper monitoring or detection of ferric ion concentration or the ferric-ferrous ratio, and use that in the control or the process control of the leaching circuit. This will also benefit in the region addition, definitely. So for this translation project, we divided that into 6 phases as well. The first one was to try and get a lab-based leaching rig on site at UniSA, where we can run or experiment what is similar to on-plant, mimic what is done in the industry, and that is done, and also do some preliminary studies on 2 ore types that we received from BHP, which is also done. So we're moving on to testing the MOF sensor once Linda has that ready to be tested in the real ore system, and develop that, then propose a next step after that test work and stability test that can be done on that. So this is how the leaching setup looks like. So we can monitor the solution chemistry whilst we are doing the leaching, and also at high temperature. And we've done initial work. Definitely, all these things are done in collaboration with Magaton. Initial work with the effects on mineralogy, and we could see that the change in mineralogy in 2 sample types affected not only the leaching yield, but also the rheological behavior varied for the two sample types. So I'll now move on to translation project 11, and this one is focused on developing a new laboratory AgSag mill, which can be used as part of research project 1. So first of all, we've been able to design the SAG mill, and that has been approved by Magatory and has been fabricated and installed at UniSA. And we've also equipped that with a sensor, and that's mainly what Kweku Owusu-Boateng in Project 1 has been using for his work, and it has been successful in commissioning that as well. So this project is complete. It started also in 5 phases, designing the mill drum, getting it reviewed with Magato and fabricating it, which was successful. It's now installed at UniSA, and we had very good commissioning. And as I mentioned, it's currently being used by Kweku for most of his studies in the lab level. So this is how it looks like. If you previously know the Magato ball mill, it's not too different in that, but then because it's a SAG system, we have a shorter length, so that's around 15, and also the diameter around 30 centimeters. And so the sensor is equipped to be at the toe of the mill, where we can measure information from the mill. And this is very important, because when on site we are not able to change so many things. You can't vary the conditions, see how that is affecting the process. But in the lab we can go extra mile. And so when BHP says, okay, check this for us or do that for us, we can definitely do that in this lab mill. And the other thing too is that, being similar to the Magato ball mill, you're able to monitor the pulp chemistry. So if that is important and relevant for a SAG system specifically, we can do that as well with this mill. So how does this all sit together? I'll copy this from Bill's slide, which he showed a bit on Sussex of that. And so when we have all these sensors in a grinding circuit, the flotation circuit, and also in the tails leach circuit, we are getting not just data. So like I showed you in the flotation modeling that we did, we can use the plant data, but the usefulness or the causal relationship between the variables is very important. So we are collecting what is very important, and from fundamental research that has been done in the mineral processing, there are some variables that are very important and can have significant impact on recovery. Most of those variables are not measured on plant. And so in real time, there's regular measurements done most cases, but not continuously. So if we have these sensors on plant, which are taking these measurements continuously in real time and are feeding into, okay, that's my alarm there. And are feeding into a given control system, we are better able to optimize the whole value chain. And you are not only looking at the processing section, but you're also getting information from upstream, the program A information feeding into that, and that can help us have a better grip on the metal production downstream. So you're moving from a less stable condition, very unstable condition, to a more stable operation, which is very stable, and you get good outcome. And that means that you're getting lower cost and high throughput, and also high metal recovery from the operation. So that will be all from me. I would like to acknowledge all our translation partners and sponsors, BHP Olympic Dam, specifically Kati, Kavita, Meredith, for their support throughout, Chris, John, for all the meetings and discussions so far, and all the researchers, CIs in PRIF, and students, Postdoc. Thank you very much for listening.
Questions?
Yeah.
That's a lot. That's a lot. Well done. Okay, no questions?
I was just thinking about your tails leach, the MOF sensor there. So Linda was saying how it wouldn't really be suitable for pH 1, that is the environment that we have in tails leach.
Yep.
But it seems as though the plan is to get it ready to be able to measure our leach circuit online. So how might that be achieved? Do we have to do some dilution, measure it on an intermittent basis, not continuous, take a dive into the tanks, and just interested in that aspect?
Yep. I want to stop here because this is the pop chemistry monitor. They're now the Magopop. So in this, if I go back a bit, probably here. Yep. So what this does is you've got a chamber there, and so the slurry goes in there and it's conditioned. You take the measurement. So what Linda was talking about, where we could dilute that or move the pH up a bit. So that gives us room to be able to do that and still take the measurement. So initially what we're doing with the translation project is to see whether when Linda is done with her work and we put it into real ore system, would that be stable enough? Would the sensor be okay to measure that? And also when we try, so we're getting different type of samples by the help of Cathy and Vanessa on site, where we have high ion concentration samples, which are not typically processed on plant, but I mean, we're trying to go the extremes and see how that can affect the sensor. So that would be what we want to do there. In terms of engineering it into the side, we can do something like this, diluted. One other thing I think Kirsten, Linda didn't mention with the low pH was a transformation to another phase. So there was another phase which was more stable at a lower pH, but because of time, she can't dive into that aspect. And that would be very interesting if it's an area to dive into, whether that phase can be able to measure the ferric ion as well. So that can work minus 2.4 the pH. So the 1 pH and things like that. So a very aggressive environment. But there's room to be able to do that. Yeah.
Any more questions?
Just going to ask you to comment, Richmond, on what were the biggest challenges perhaps in getting the translation projects to their current stage?
I think everyone now can blame COVID. Yeah, so it's been one of the big challenges getting to site, especially last year. So last year, when the COVID came up, going to site became very difficult. And it's understandable to be able to get the sensors up, change things as are required, and that delayed us a bit. But like Cathy mentioned, getting the right info conversation ongoing with plant, knowing what is required, what they need, and things like that, that's also very good. So, but a major challenge that has affected is COVID-19. And that has delayed a lot, but with the extension that we've received, that is anticipated to be addressed going forward, so we can get a lot done. Yeah.
Yeah, indeed, we hope so. I mean, that was the basis of the extension request, and yeah, it's been granted, and we've still got 15 months to get data. So let's see. Thanks, Richmond.
Yeah. Okay.
Thank you very much. So thank you very much to the speakers from Program B of the consortium. We'll now open it up if anyone's got any questions for any of the presenters from Program B. Please speak now.
Do we have anything online, maybe?
No. If that's the case, I will present these on behalf of Tatiana to Nigel.
Thank you.
Yes, I'm very. Thank you.
I guess I'm too. Thank you very much indeed.
And we'll now get Professors Nigel Cook, Peter Dowd and Bill Skinner up onto the stage for the wrap-up and panel discussion. Onto, yes. It's not that sort of event, Nigel. So maybe come up the front, and Nigel, you can pass your microphone around to answer questions, and Yerniaz can be the roving mic again in the audience. And of course, if anyone's got any online questions, just add them to the Zoom chat. About 20. It's been consistent throughout the day. Nigel, take it away.
Okay. All right. Well, I guess I'm going to just first of all just say a few words of thanks to various people. I'd first of all like to thank our guest presenters for today. We were very privileged to have that wonderful lecture from the chief scientist this morning, and to hear also Gavin's insights into what can come after the consortium. So thank you very much for that. But I would like to thank all of our presenters today. I think it was really a wonderful show of excellent high quality presentations, and for me personally, very good to see all the significant advances, really sort of practical advances that have been made over the last year. Looking back to the annual assembly that we had last year. So well done everybody, you've really done extremely well, and enjoyable presentations, and you know, I really think we did the consortium proud today with those. I'd like to thank the audience for their questions and the discussion that we've had. I'd like to thank the online audience. I know it's been a little bit difficult. You haven't been able to see us. We haven't been able to see you, but it's been great to have you there and to know you have been attending today. I'd like to thank the Wine Centre for their support and for the food, drinks and refreshments. Been extremely good indeed. And our AV team that have been behind the scenes there, making sure that everything runs smoothly. Somebody else I'd like to thank specially is Damia. If you maybe want to stand up, Damia Eta Katumi. And Damia has been actually very influential in this assembly, because last week we had a media training day, and all the students got training and comments on their talks from Damia as a professional coach. And you could really see today how it rubbed off. So well done, Damia. And she's available for bookings. Just contact her. I'd also very much like to thank BHP Olympic Dam, and particularly Kathy Eric, not just for being here today, but for sponsoring today's activity here at the Wine Centre. So we really appreciate that on behalf of the consortium, and your continued involvement in everything that consortium's doing is really, really deeply appreciated. Couple more, I'm almost done here. I'd like to thank Ruth very much indeed for being our Master of Ceremony today. You really have outdone yourself. You've been a superb Master of Ceremony and have handled everything extremely efficiently. There's somebody else that we do need to thank very much from the bottom of our hearts, and that's Tatiana, because without Tatiana, today would not have happened. She has organised and cajoled and prodded and reminded me on at least 57 occasions, I think, of various things that need to be done, and really made this happen with absolute fantastic, detailed organisation of today's event. So Tatiana, thank you very much for being there for the consortium. You really are the rock of this consortium, and we all deeply appreciate your efforts.
Come up here. Come up, Tatiana. I think I heard the champagne pop.
Certainly, on behalf of the consortium, then thanks very much for having a wonderful day. But perhaps before we finish, we just pass over to think about what we've heard today and what it all means and how the consortium goes goes forward. Perhaps I just pass over to Peter or to Bill to say a few words.
One of the things that it's made this project incredibly enjoyable is the full engagement of the industry and translation partners. It's been really excellent. I mean, especially when COVID hit last year, every effort was made to try and find other avenues in which to progress things forward, whether it was additional data from somewhere or other help along the line, computing, all this kind of thing. So I really want to thank the industry partners and the translation partners for basically being fully engaged with this, and I think that was it's actually quite unique. I don't think I've ever been part of any project that's been so integrated, right, in terms of actual buy-in from both the industry partners. So thank you to all of you.
Yeah, I suppose with very large projects like this, you start off at a given level with, I've forgotten how many there are in terms of individual researchers involved, but quite a lot. And there was a time there where it seemed to me that we were going like this, then we were going like this. And that was when we were having separate sessions for Program A and Program B. And I'm really pleased to see today we've finally come like this. And you have everybody in the same room talking about the same things. And I think the more we do that, the better it becomes. Of course, there's lots of disciplines involved in this, and I'm only involved in one particular discipline, and I guess most of you are only involved in one, but maybe two or three. But to see all of those disciplines being presented in a way that probably the person who came in off the street could understand a lot about it, and certainly allows everybody else with different discipline backgrounds to understand what's happening. And I really wish we'd done that right from the start. But given that we've done it now, that's good. And we've got another year or so to go, and I hope that we can keep this momentum going. So well done, everybody.
Thank you, Peter. I really echo those sentiments about actually getting everybody together from the outset. We should have done that. Okay, I'm not going to say much more apart from the fact that I think my acoustic sensors are hearing the clinking of glasses at the back of the room there. So I guess I'll pass back to Ruth now to just wrap things up.
So thank you for a wonderful day. And please enjoy the rest of the afternoon over drinks, canapes and networking, and your last chance to check out the consortium posters. But before you're allowed to get a drink, we want to get everybody up here to get a group photo. So no drinks until you get a group photo. There's always a catch. Up you come.